Thank you for your kind introduction. First, let me thank to the organizer, particularly Saikat, Bimalendu and Sourav, to give me opportunity to present our work here. Today, we are going to talk how to control the diffraction and rotation in an atomic medium. Basically, if you have a geometrical structured beam, when it propagates through the medium or free space, inherently it will have a diffraction. So diffraction kills your information, and here we are trying to understand how to eliminate this diffraction and send the beam from one point to another point at a length, let us say 20 of the Rayleigh length. Then you can do the fruitful communication from one point to another point. Here, what we are using, that fold level system that we are going to discuss. And overall, when you are going to control the amplitude, polarization, and the phase, then you are going to control over the full structured beam. And this full structured beam give you the infinite Hilbert space. Only the vector beam is going to give you the infinite Hilbert space, otherwise not. So it has a great advantage, as well as it has a great applicability in the super resolution. Since when you talk about the vector beam, you have a polarization singularity, and if you have a transverse as well as the longitudinal polarization control, this longitudinal polarization control can be minimize your spot size and beat the resolution limit. So let us first develop what is the beam propagation equation. We are going to start from the Maxwell equation, 4 Maxwell equation, and we know this is a Gauss divergence equation. Del dot D is equal to 0 and del dot B, and then you have a del cross E is equal to minus 1 by C del del T of B, and this is your Ampere's law, del cross H is equal to 1 by C del del T of D. You can see we do not add any source term like a charge or current, since we are working in a medium or free space where there is no charge, no current. Now we have to be very careful about the material equation, because we are going to use this material, any material as an induced polarization. So therefore the electric displacement current D can be written as a E plus 4 pi P, and the B is equal to H plus 4 pi M. And here what we are going to do, since we are going to work in a non-magnetic material, so therefore you can take M is equal to 0. Now what we are going to do next, we are writing the electric field in terms of the scalar and vector potential, and develop this vector potential wave equation del square A minus 1 by C square del square A del T square, under the condition that it satisfies the Lorentz gauge condition. And this condition is going to fix the polarization of the photon. So photon has a 2 polarization, sigma plus or sigma minus. Therefore you can, from this equation you can decide that photon has a rest mass 0 or almost 0, and also it has a 2 polarization. Now in order to solve this wave equation, we are going to assume the vector potential as a form like a plane wave form, and it carries a angular frequency omega, and it propagates along the z direction. So and it has a polarization along the x direction. Now what to do first? First we have to calculate the magnetic field, and assume that we are working in the slowly varying envelope approximation that I am going to show you here. So in this, what I did, we are going to calculate the B is equal to curl of A, and then what we are going to do this approximation, slowly varying envelope approximation, that is K times U very greater than K square times del square U del Z square very greater than del square U del Z del square 2 Z. That is the variation of the space in second order is very negligible. So under this condition, wherever you have a del U del Z or del square U del Z del 2Z, you can neglect it, and you are going to get a magnetic field expression in this term. Once you know the magnetic field, you can use the Faraday laws or you can use the Ampere's law to calculate the electric field, because del cross H is equal to 1 by C del T of D. So let me show you here. So you can compute the electric field, and here you can see there are many derivatives, and second order as well as the first order. And then what you can do, you have to neglect this term, the second order derivative as well as the first order derivative. So under this condition, sorry, this is a mistake. So you should not read Carl of Carl H. He said Carl H only. So now under this condition, if you see, right, the electric field structure, you can see E is equal to I k x hat U plus I by k del U del x of Z. So you have there is a variation along the Z direction, right? And you can see this is possible. Initially, you can think that electric field and magnetic field is not perpendicular in presence of this variation, but this is a real laser field equation. So you can accept this, the field governed by this equation. Now let us calculate the Poynting vector, time average Poynting vector, because when electromagnetic radiation propagates from one place to another place, it carries the energy and the momentum. So in order to calculate your the energy and momentum, we are going to use this Poynting vector. S is equal to C by 4 pi E cross B star. So then you can see in the Cartesian coordinate system, you have the momentum along the Z direction, but it is not very clear which direction. In order to clarify what are the direction involved in this Poynting vector, so what we are going to do, instead of the plane wave solution, I am going to take a logarithmic Gaussian mode. So logarithmic Gaussian mode has a three dependence, R, phi and Z. This is a longitudinal direction, phi is the azimuthal angle, and R is the radial vector. So if I substitute this U here, then I can see I have a three distinct parameter. One is the SR, that is the radial variation of the energy. S phi, that is the azimuthal variation of energy, and then SZ. And you know that SZ is a linear momentum. But what is the SR? SR is the spreading. When any beam propagates in a free space or medium, it is going to diffract. So it is a spread along the R direction. Now what about this S phi? It carries the angular momentum, and it is because of the Professor Allen who invented that angular momentum is a very crucial parameter for the beam. So now here is the propagation direction. So you can see it is a helix. So momentum is carrying along the Z direction, and you have a helical path. So if you see the phase font, okay. So before I show the phase font of this helical path, let me tell you what is the correction term you need when you have a medium. Whatever I have told you, it is a free space. Now, in order to incorporate the medium, you have to take care of the induced polarization. So if you want to introduce the induced polarization, then you have to define the induced polarization, because induced polarization is nothing but it is a presence of the incident electric field. So whatever the electric field you have a structure, the induced polarization have a same structure. Now, if you substitute here and do this slowly varying envelope approximation, then you are going to end up with this equation. So you have the longitudinal variation associated with the transverse variation, and that is the main culprit of the diffraction. If you nullify this term, so you can see that you can propagate the electromagnetic energy from one place to another place without any diffraction, provided your susceptibility, imaginary part of the susceptibility part goes to zero. Otherwise, you cannot transmit the energy from one place to another place. So therefore, so you have to engineer this sky in such a way that the real part of the sky can compensate this diffraction part, and imaginary part of the sky should be zero. As the Professor Shankar told you that EIT is the best mechanism to make absorptive medium to transparent. So you can use this EIT technique to suppress the absorption and get a high intensity at the output end. So up to this point, everything is very clear, but this is the story about a scalar beam, but vector beam has a two component, right? So the controlling about the two component is very difficult than the one component. So because it can seize the different detuning, it can seize the different rotation. So you have to be very skilled to engineer the medium. So let me show you that thing. So here, what you have, so when electromagnetic radiation propagate, some of the radiation is rotating along the z-axis, and that beam or that electromagnetic radiation carries the angular momentum. And you have, in general, you have a two angular momentum. One is the spin, like if you have a photon, you have a positive helicity and negative helicity, and then you have a orbital angular momentum L. And N can take any value. L is equal to minus infinity to plus infinity. So you are going to get infinite Hilbert space. So now, what we are going to do here we are going to define the logarithmic Gaussian beam. First is a scalar beam. So you have only one direction of vibration, that is the linear vibration, and you have a r phi z, and this is the logarithm polynomial, and you can see this beam has a waist omega z, and it is just dependent upon the propagation length, and it is dependent by this relation omega 0 root over 1 plus z square plus z r square, where z r is the Rayleigh length. And after the one Rayleigh length, this omega z becomes square root of 2 times of omega 0. So it is going to diffract. So now you can define also the Gauss phase, right? It is very interesting for the polarization singularity, right? And then what we are going to do, this is a scalar beam. We are going to see the wavefront. Here if you have a m is equal to 0 and p is equal to 0, that will give you the Gaussian wavefront. It's like a plane wave. Then you can see that at the center, line center, you have a highest intensity. So it is a uniform intensity across, right? And then it is going to take say envelope of Gaussian wave. But when you change the m to +1 or -1, you can see the singularity, and that will give you the Riemann surface. Means you have a singularity around this point. And then if you take m is equal to 2 or -2, you have a 2 singularity. This is the Riemann surface, and you can see there is a 2 helical beam propagating along the z direction. So now, yes.
Why space can you get also the momentum in the z direction?
Momentum
K in the z direction.
K along the z direction. Momentum is there. Momentum is there in the previous calculation.
Along the pointing, sorry, not
pointing
vector along the z.
Yeah, then you have to tilt it, and then there is a lot of messy calculation, right? Here what we want? We want in the z direction. And if you have a little bit tilted with the z direction, then you have a different inhomogeneous wave vector. So that is a little difficult question. Okay. So otherwise, you can do it. In principle, you can do it. And in that case, the intrinsic angular momentum can be separate from the extrinsic angular momentum. Okay. Okay. So now, let me tell you the one experimental result done by the Professor Sanjay. And here, what he did, we know that lambda system already so many speakers have told you. So in the lambda system, we used to use two kind of beam. One is the control field, another is the probe field. And we consider probe field is weak and control field is strong. And then what we are doing, we are manipulating the medium dispersion for the probe beam by a control beam intensity. But in this problem, what they did, they considered both beam are weak beam, and there is a no intensity, very low intensity. Then they are trying to see whether the phase information can be mapped to the amplitude information or not. Basically, phase can be mapped to the intensity or not, and that they have achieved. What they did, they considered L is equal to 2, that is the angular momentum. When you have L is equal to 2, they have a 4 spatial bright spot, and this 4 spatial bright spot signifies that you created 4 EIT transparency window at those positions. So therefore, when you change the L value, the angular momentum value, you can also change number of transparency window in the spatial domain. So therefore, the phase can be mapped to the amplitude. And this is their experimental result. We have done a rigorous calculation, and what we did, we considered two weak probe field G1 and G2, which is coupled between the 3 and 4 and 1 and 4. And these two are the electric dipole allowed transition. And you can see the 2 to 4, it is electric dipole allowed transition, but it is a bipolarized light. So when you have a sigma plus, it will couple to 1 to 4. When you have a sigma minus, 4 to 3. Now, when you have a coupling this thing, now in presence of the magnetic field, and magnetic field has a two component. One is the longitudinal component, another is the transverse component. So longitudinal component, what it does, it will give a shift from the two level. Basically, it is an energy shift, but the transverse component has a beautiful characteristic. It will do the population redistribution among the 1 and 3. So if you have a control about population redistribution, then what you have, you can effectively control the susceptibility of the system. So now here you can see that initially we have sent a logarithmic Gaussian beam as a probe beam. Then finally, after a length of, let us say, 2 Rayleigh length, we have the spatially structured beam. So you can see that this is the spatial structured beam, and this the spot size is less than the super resolution what it is the limit. So you can create a spot size less than the Rayleigh limit. So next, what we are going to do, this was the story of the scalar beam. Now we have a vector beam where we have a two component. This is the left circularly polarized light and right circularly polarized light, and then everything is the same, but you are going to create a polarization inhomogeneity along the wavefront direction. So how you can do it? Already Professor Ghosh has told you that with the help of the Q plate or the SLM, you can generate the inhomogeneity in the polarization direction. So now let me show you, before you compute the polarization quantity, like if you follow the Jackson description, Jackson has defined that S0 and S3, this is basically a intensity, sum of the intensity. It is a difference of intensity, and S1, S2 gives you the, S2 is going to give you the polarization angle, and S3 is going to give you the wanderness of the X polarized light over a right polarized light. Now we can define the ellipticity, because for a general polarization is the ellipse polarization. So when the ellipticity zeta is equal to 1, you have a circle. If zeta is equal to 0, it is a linearly polarized light, like you can define. And then ultimately we got this analytical result. And it depends upon the, you can see the variation of the angular momentum, L, R, and L. If the L or L are the same value, but then what you can see, there is no rotation due to this angular momentum. If it is a different value, then also as a no rotation, but you have to choose like a cylindrical vector beam. When you have, it has a two component, and both the component has a LL is equal to LR is equal to 1 plus or minus. In that case, it is 0. So rotation comes solely from the refractive index variation. What is the refractive index variation? Delta NRL. So what is that? The refractive index for the R component minus refractive index of the L component. And if this NR minus NL is non-zero, then you have a rotation in the polarization structure. Otherwise, you cannot get a rotation. Like in free space, if you have a cylindrical vector beam, if it propagates through the medium, right? This free space means medium means here free space, then it will rotate. Okay, and same cylindrical vector beam, if you propagate through the medium with a refractive index NR is equal to NL is equal to some magnitude, then you will see that it can rotate. So by changing the refractive index, you can manipulate the rotation of the polarization. Now, what we are going to do here, Professor Bob Boyd has shown that in the rubidium vapor, they have sent a two beam, and this beam is generated by this PBS polarization beam splitter and this λ/2, λ/4 plate as well as the quarter wave plate to generate this inhomogeneity of the polarization and then propagate through this atomic vapor. And what they get when alpha, that let me show you the alpha. Here we have defined alpha. Here, this is the inclination. If alpha is equal to 0, then what it will happen? Only you have a one component. If alpha is equal to pi/2, another component. If alpha is equal to not equal to this 0 or pi/2, then you have both the component. So this instrument is going to give you the alpha value, and then what they have done, when alpha is equal to 0, this is a basically linear polarized light, and if they see the transverse profile as well as the polarization profile, it can show you there is a distortion. How do you eliminate that distortion? Here also you have a distortion. So alpha is a polarization case. Similarly, when alpha is equal to pi/8 and alpha is equal to 3 pi/8, also you have a distortion. Only alpha is equal to pi/4, you have a no distortion. So therefore the question is that for their case, it has a lot of absorption because the medium is not transparent. So how to manipulate first transparency, then next how to control the diffraction, and third is how to control the rotation. So it is a lot of work to do. So what we have done here, we consider a tripod system. And here, what we are going to do, we apply this vector beam omega r, omega l, which will connect between 4-2 and 4-1, and another control beam omega c, which will connect, it is an electric dipole, and it is a sigma c polarization, so 4-3. So now what we are going to do, earlier we have given a magnetic field, which is a combination of longitudinal magnetic field as well as the transverse magnetic field. Now what we want that only this phase shift, and because of this energy shift, we are using only the longitudinal magnetic field. We do not introduce any transverse magnetic field. If we introduce the transverse magnetic field, then population will reshuffle from 1 to 3. Okay, then there is a no trapping state. So then what we are going to do here, so we have to do a little bit mathematics. Sorry, this you have to define the Hamiltonian in the proper unitary frame, and this is the we have to do a little bit unitary operation in order to make this Hamiltonian time independent explicitly, and then you take this density matrix formulation and end up with this calculation. Like this calculation is important because if you go back to your the level system, we are going to very much worried about 4-1 transition and 4-3 transition. So here we have done a perturbative calculation and get a coherence 4-1, and you can see that this 4-1 is quadratically dependent on this control beam as well as quadratically dependent upon the other two components. But when the probe field is weak, two component is weak, then these two component is negligible. Male component is omega c, so transparency you will get it. So now under this condition, if you also this other component has the same kind of structure of this coherence, and then under this condition, if you see the susceptibility expression as a function of detuning, then you at a line center, or you can see the beta L. Beta L is the magnetic field. So this beta L is equal to 0. Then at the line center, you can see there is a transparency as well as your refractive index also 0. So you cannot get a rotation. So therefore, you have to be very sure that you have a refractive index non-zero as well as the transparency window. And then what we have increased the control field intensity in order to get a flat bottom kind of window. So at this region there is no appreciable absorption, and then you can see there is a non-zero refractive index. So now, if you this is the story of this right-hand polarized light. Now let us look at the left-handed polarized light. Same nature but opposite. So now you can see you have the delta NR, which is the difference between NR minus NL. So if you are working here, right, that NR and NL difference is large. So you can get a large rotation. So now what we do? So you can manage the rotation, but how do you manage the diffraction? Right? That is the next question. So what we did? We apply the control field with a special profile, and the special profile is a basal beam. So here basal beam is a non-diffracting beam within the medium up to 50 Rayleigh length. Okay. So when you have this basal beam, then you can see that your refractive index, you can see the refractive index is high at the x is equal to 0 and low at the wings, and you can see here it is a gliding effect, here is the core effect, as well as the absorption is 0, right? So our job is done. But this refractive index profile, here I am showing you that right-handed. Now for the left-handed you have a reverse refractive index. So inside core, right? Instead of core, it is become a gliding because here is the core. So the left-handed cannot be guided. So therefore, again, you have to manipulate in such a way that you have to choose the parameter of the control field in such a way that both will see the center at a core and the wings would be the gliding. So if you meet this criteria, then you propagate the beam without any diffraction. So what we did here, instead of delta C is equal to 0, we have changed delta C is equal to 0.2 gamma, and then you can see the right component also see the core and as well as the minimum absorption, and you can see left component also see the core as well as the minimum absorption. So here is the story completed. Now what we did, we just instead of this basal Gaussian beam for the control field, if you consider the CW field, that will not going to happen. Here is the case because here the refractive index is constant. Here also the absorption is a little bit high. So now let me consider this cylindrical vector beams, and then we are propagating in a free space, and you can see that if it is a 0 phase, here it gathers a pi/8 phase, and it is consistent with our analytical result after a length of z is equal to zr. Now when you see the spatial variation or transverse profile of the this profile, you can see it will diffract much. It is not concentrating on the core. Core means the around this point where it is intensity is maximum, like a x is equal to ±1. So now this diffraction comes due to the free space induced phase to this constituent wave, and therefore you cannot eliminate this free space propagation diffraction free. In free space there is no beam which can carry the energy from one place to another place without diffraction. Only some of the beam. That beam is the Matthew beam and basal beam. These two beams can carry without diffraction. So now it is a when I have this atomic waveguide, you can see this is a core and the outside ring behaves as a gliding. So therefore we have reached this geometry. Similarly for this other component, in that here I explained that how this delta C, when delta C is a 0.2, one can push the line center not at beta L is equal to 0, but it is away from the 0. So you can just manipulate the refractive index whatever you want to. So this is the criteria. Now here also, now this is the last my slide. What we did, we considered the Gaussian beam and radially polarized light. Now this is the profile, the spatial profile at z is equal to 0. Also you can see at z is equal to 4 ZR after Rayleigh length. What you can see, the spatial profile, intensity profile is intact. There is no diffraction, and this radially polarized light this is a azimuthally polarized light. So you can change the polarization. You can change the polarization rotation by applying the magnetic field, which induce the anisotropy. And you can see the field intensity concentrated at the core only. There is no diffraction up to whole Rayleigh length. So here the story of non-diffracting and polarization control of a vector beam. Thank you for your kind attention. Okay, let me okay, just a moment. Let me thank Nilamuni Doloi. This is his work in PhD work. Also, I would like to acknowledge the funding from ACRB. And this work has been done with the collaboration of Pardeep Kumar. He is in the Max Planck Institute for Science and Light. Thank you.
Questions?
When you say that left-handed, right-handed have different refractive index, is it mean that absorption coefficient will be different in that case for both the light?
Absorption coefficient would be the same, but the refractive index is different. Let me show you. Yeah. Let me show you. Here, can you see that this peak, double peak curve, the absorption is same, right? And it is a rho 4-1 or Karik 4-1. And similarly, you can see the absorption profile are same, but the refractive index, right? That is the real part. You can see it has a what it is. It is a positive slope, but the previous one is a negative slope.
But if you have an optically active kind of system,
Optically active kind of
mediums,
system, gain system, yeah, you can
then
also,
you will get
yeah, same kind of
similar
things,
kind
yeah,
of things,
because it is absorptive. Just you can think about the gain medium, but gain medium is an advantage because you can compensate the loss of energy during the propagation, right?
I think we have an online question.
Yeah, please.
Check. Online question open.
What happened?
Hello. Hello.
I think there is.
Please.
Tarak, I had a couple of questions.
Yeah.
So the point here is that when you focus a beam, my question is, first of all, what is the W0? What is the width of the beam as compared to the wavelength? First clarification.
Yeah, let me answer first this question. The waveguide width is almost 30 micrometer. And by changing the width of the control beam, you can change the width up to.
Question is the beam, the vector beam. What is the spot size of the beam at the focus?
Yeah, that's why I am telling you that is spot size. You can see from this figure. Yeah, here. So sorry, here I did not mention the scale.
Just tell me approximately. Tell me what is the ratio? 1:10, 1:20, something like that. Wavelength versus this spot size.
Wavelength versus spot size. Okay, so it is 1 by most probably 1/20.
1/20. Now,
Yeah.
if you focus a beam like that, of course, there will be this longitudinal component. You'll be having this transverse spin also.
Yeah.
So I didn't see any discussion of transverse spin in your picture. So you are looking at, you are assuming that this longitudinal component is not there or something, this transverse spin doesn't arise in your problem?
Actually, we did not look into that problem. Okay, this longitudinal
So
part.
you are ignoring completely Bimalendu spin, right?
Yeah, right now we are ignoring, but later on for super resolution, we definitely discuss this problem.
I see. Okay. And these other Stokes parameters, people often do this Stokes mapping and everything.
Yeah.
If you really look at the issue, polarization is defined only for plane waves, not for beams. Okay.
Yeah.
So only for plane waves, you define EY by EX as a quantity that you say, depending on that, whether it's real, imaginary, or you decide whether it's a circularly polarized light or linearly polarized light.
Yeah.
Now, when you talk to beam, are you talking about different spatial K components and then the spin state or polarization state of those spin components? That is your polarization.
Yeah, you are right. You are right. You are right. Yeah.
So that's the way you are doing the Stokes imaging, right?
Yeah.
For different case.
So different case.
Harmonics.
Yeah.
Oh, I see. Okay. And the other question is that is there any deformation of the beam or not? Let's say you let the probe be a little bit stronger. Now, will there be
we have a saturation effect, means power broadening kind of things.
No, power broadening is for very large powers. I'm talking about much before that.
Yeah.
Because the spin is a very tricky issue. Spin can spoil everything, right? So does it affect the shape of the beam?
That we did not explore. We are right now all in the linear region. So if you enhance the probe intensity, definitely the nonlinearity comes into the picture. Maybe like Professor Boyd here, they showed that there is a distortion by enhancing this power, and that distortion may come. Okay.
Okay.
Yeah. Here, sorry. Let me show you. Just a moment. Hold on. Here. You can see there is a distortion here, also here, and they are solving the saturation absorption spectroscopy, and they did not consider that absorptionless medium, and also they considered the intensity effect. You can see from this last term of this paraxial wave equation that intensity effect is going to give you the distortion of the beam.
I see. One last comment. Actually, this when you talk about this thing, this kind of beam propagation, which has a structure as well as which carries this angular momentum. But was that this EL and ER? There was a phase difference between these two? No.
EL and ER, initially we gave the phase difference, but that phase difference doesn't alter. We have proved that thing throughout the length of the medium.
Oh, I see. Okay, thank you.
Thank you.